Hey guys, welcome back. If you're watching this video, I'm assuming that you all are data enthusiasts interested either in data analytics or data science and AI. Now, whether it is data analytics, data science, AI, whatever it is, cloud computing, DevOps, anything, everybody should be aware of SQL database and NoSQL database. I am assuming that everybody knows about it. In case you are a complete beginner with without having any knowledge in SQL, just write down SQL in the comment section and I will enroll you to my SQL course completely for free. Now coming back to the topic. When it comes to databases, there are majorly two types of database, which is SQL database and NoSQL database. Now talking about SQL database, there are some databases like Oracle SQL, MySQL, Postgres, Google BigQuery. These are all SQL based databases. And talking about NoSQL, Cassandra, MongoDB, and multiple other things. Now, with all of these generative AI things popping up and all of these changes happening in this world, there is a new concept called as vector database, which we have already covered in some of our previous long generative AI videos. But in case you have missed that point, in this video I'm going to talk majorly about the differences between vector indexes and vector databases. So in case you are aware of some of the generative AI topics, some of the generative AI concepts, and you're interested to know more about vector databases, even if you don't understand generative AI in generic terms in general, if you want to learn more about what a vector database is, what is a vector index, then watch this video till the end and I'm pretty much sure you will be able to understand all of these topics within the next 1 or 1.5 hours. And in case you are interested in the generative AI ebook, let me know in the comment section. Just write ebook and I will be sharing you the generative AI ebook to you as soon as possible. See you in the video. Hi, let's talk about vector databases. One of the most important topics when it comes to large language models, because eventually our data has to be stored somewhere, right? We are going to use huge corpuses of data. Somewhere it has to be stored, because once it is stored in some location, when a user is asking a question, it should go and refer to a particular location, right? And then from that location, it should get some feasible output, and using the chat completion technique, it should be able to get the final response, right? Where do we store these databases? Can we use a traditional MySQL database or a traditional Oracle SQL database? Well, my simple answer is no, because traditional SQL and NoSQL database will not be able to store vector data. First of all, let's try to talk about what is vector data. I think everybody has already gone through basics of NLP, and of course, we have covered NLP till the advanced module. At least, if basics is clear, you will be able to understand, right? What is vector data? Vector data is simply text converted into numbers, right? Numbers are nothing but vectors, right? Some of the word embedding technique or some of the vectorization technique is, let's say, word to vector. I will recommend, if you have not gone through the practicals and theoretical part of word to vector and various other topics related to vectorization, please go back to NLP basics, try to understand and come back. In this video, I'm going to give you a brief idea, not in-depth idea, right? Let's say vector, word to vector is basically a Google based model, right? Which internally has around 300 features, which are created by neural networks out of 30 lakh words, right? I hope everybody knows about this. Let's say I'm talking about a vocabulary of 5 words. Okay, let me scroll it down. I'm talking about a vocabulary of, let's say, 5 words. I cannot take more words, it will be confusing for you. So I have taken a vocabulary of 5 words. Okay. Let's say I have king, I have queen, let's say man, woman, and elephant. Here I have features, right? So let's say I have some features. Let's say my first feature is gender, my second feature is money, my third feature is power, my fourth feature is weight, and my fifth feature is let's say speak. Gender, king is gender, male gender. Let's say I'll give 1, queen as 0, men as 1, woman as 0, elephant, let's say male elephant. Okay. Money, how much money that the king has? Lot, right? Queen also has a lot of money. How much money the man has? Let's say I'll talk about an average man, so let's say 0.3. Woman, let's say I will not differentiate, else we'll talk about gender equality. 0.3. How much money does the elephant has? 0, right? Power, king has more power, queen also has great power but not as powerful as king, right? Let's say men are around zero point 0.2, women are around zero point 0.2. Power, yeah, elephant has quite a bit of power. Weight, let's say king is 0 0.8, queen is lightweight 0 0.4, let's say man is somewhere around 0 0.6, woman is somewhere around 0.5, and elephant is 0.9. Speak, they all can speak, yes, so everybody has one. Let's say element is 0, right? Now what is the vector representation of king? The vector representation of king is 1 1 1 0 0.8 1, right? I'm talking about this thing. What is the vector representation of man? 1.3, 0.2, 0.6, and 1, right? What is the vector representation of woman? Woman is 0, 0 0.3, 0 0.2, 0 0.5, and 1. Okay, let's say we will do some mathematical equation, king minus man plus woman. So let's say what will be the final output? King minus man, 1 minus 1 0 0 0 0, 1 minus 0.3 is 0.7 plus 0 0.3 is 1, and 1 minus 0.2 is 0.8 plus 0.2 is 1, 0.8 minus 0.6 is 0.2 plus is 0.7, 1 minus 1 is 0 plus 1. What is the vector representation of queen? 0 1, 0 0.7, 0 0.41, right? You can see it is almost relevant. So you can also tell as king minus man plus woman is nothing but queen. Okay, approximately, right? Not exactly, but approximately, right? So normally when LLMs are created, right, when you're passing a custom data to LLMs, your custom data could have a millions of text, millions and millions of text, lot of words. Eventually I'm talking about millions of vectors, millions of vectors, right? Can we use a traditional database? Let's say we use a traditional database. Let's say I'm using a MySQL database. Okay, imagine how many vectors are possible. Millions of words, will actually create trillions of vectors. Okay, so let's say there are trillions of vector data here. Now as a user, I'm asking something. Okay, let's say my question is, what is ADA? Okay, I'm basically asking from the document, and let's say I'm training a ADA related document. Now what's happening here is, my bad. Oh, you're not able to run this, my bad. So let's say there is nothing here. Okay, what is ADA? So what's happening is you're converting this into vectors, right? Let's say anything, 0.3. Now from here, you're actually going and doing a semantic search over trillions and trillions of vectors. And people who have worked with SQL databases, they know how tricky it is going to be to get just one response of the common vectors or the most similar vectors from this existing database could be a nightmare. And then eventually from there, you're basically passing it to your LLM for chat completion, and then you're finally giving the output. So just for one question, your latency time could be very, very high, right? LLM already takes some time to respond. Like 3.5 generally takes around 3 to 4 seconds. Uh, uh, GPT-4 takes some more seconds, right? Now, if the latency time increases, just imagine your user is basically talking to a chatbot, asking a question. Question is being converted to vectors, referring to your MySQL database. Latency time is high, so eventually after 30 or 40 seconds, the users are getting answers or the response. Is this feasible? Definitely not. And that is why we do not opt for traditional databases. We usually go for special vector databases. Okay, so when you are asking a question, what is EDA? What's happening is, internally you're taking this as an input, you are generating the embeddings. Embeddings means you are getting the vectors, right? And then from the database, from the vector database, you're basically doing a cosine similarity and getting the answers, or getting the most relevant vectors, and basically from there you are getting the answers. Okay, so here in this part, in the search part, in the cosine similarity search part, here basically it's a linear search plus it is time consuming, especially this part. That's why we do not use our traditional MySQL databases or Oracle SQL databases. So that's why for this part we use a vector database. Okay, so in vector database, how does the storage happens, like why it is fast? Well, I told you it is fast, right? It is faster than this, but how? So let's try to understand. Usually, of course, I will show you some examples of Pinecone on how the vector data are being stored, but try to get a basic idea, right? When I'm talking about vector database, in vector database, you basically have different buckets. Tons and tons of buckets are there. So let's say your input query comes in, you have a hashing function, okay, and based on that you found that you're able to get the answer from here. So here it is not needed, here it is not needed. So you're basically going through a smaller chunk of component, more smaller chunk of bucket. This is also called as locality sensitive hashing. locality sensitive hashing, which is being used by vector databases. Okay. Of course, we will be doing a practicals on vector database. We will show you how vector databases are used. Um, so that's basically the generic ideas behind vector databases. Hi, let's talk about the next topic, which is vector index versus vector database. Okay, now if I go back to my Google Colab document, which we had gone through in the rags, right? Um, that's pretty okay. We have this. If you remember the research paper based practicals that we did at the end of the rag module. So here what's happening is I'm using FICE, right? You can see I have parsed my document. I have converted the document into chunks, and then I'm directly using FICE as a similarity search, and then I'm directly getting the answer. So basically, in none of these codes, I have called a database and I'm not storing my PDF contents in any kind of database. If I'm not storing anywhere, I'm not storing the contents of my data set. If I have to store, I have to store it in a vector database, right? But I'm not storing anywhere. You can see I've just loaded the document, used some recursive character text splitter, got it into chunks, and then I'm passing the chunks here, and then I'm calling the OpenAI embeddings, and then I'm calling the files from documents. That's it. Like, there is no code where I have called a database or I have pushed the data, the chunks, the vectors into anything, right? So here in this particular example, we are not using a vector database. We are using a vector index. But what exactly is a vector index? And what is the difference between vector index and a vector database? So let's try to talk about it. So everybody is clear about vector databases. Normally, let's say you have a context, right? You are basically converting the context into embeddings, right? And then you are, let's say I'm writing it as vector embeddings, and then you are storing it in a vector database, right? Vector database. And from the application, let's say the front end, the user is asking a question. It again goes through embeddings, vector embeddings, and then again goes through this, and from here you basically get the final output, right? Or the query results. But in this example, I'm not using any vector database. So what I'm doing, I'm basically using a vector index. Okay, now what do you mean by vector index? In this case, I'm using FICE, right? FAISS, which is nothing but Facebook AI similarity search. Okay, standalone vector indices like FAISS can significantly improve the search and retrieval of vector embeddings, but they lack capabilities that exist in any database. Vector databases are obviously better because they are physical databases where your main purpose is to manage the vector embeddings, providing several advantages. But vector index is not a database, it is just an index, right? You can think it as a local in-memory database. Okay, what is the advantage of a physical vector database or an actual vector database? There are obviously multiple advantages. The first advantage is database management. Okay, so I will write it down as DB management. What do you mean by database management? Vector databases offers well-known and easy to use features for data storage like insertion, deletion, etc., etc., and also updating, right? This makes managing and maintaining vector databases easier than using a standalone vector index. Obviously, you can also have a better debugging facilities in vector databases. The second important thing is metadata storage. Technical people do not have to worry about, do not have to um, think about metadata. I think you already must be knowing what a metadata is. Let me do it here itself. Okay. Metadata storage and filtering. So vector databases can store metadata associated with each vector entry. So each vector that enters here, we can store the metadata. Users can then query the database using additional metadata filters for finer grained queries. Obviously, the most important advantage is scalability. If you are looking for an actual application, generative AI application, 100% you should go for a vector database because there are scalability issues working with indices. If you are working on real time updates, real time, obviously, vector databases are preferable. Vector databases often support real-time data updates, allowing for dynamic changes to the data to keep results fresh. Whereas standalone vector indices like FICE or ChromaDB, they uh, they may require a full re-indexing process to incorporate new data. Obviously, when you are using vector databases, there are no concerns around backups. Your data is always safe. But in indexes, if something goes wrong, your system gets rebooted, if your index is being deleted by some user unknowingly, then your information is gone. You again have to rebuild the indexes, which is again a time taking process. Okay. Data security and control can also be one of our options. Security or data security, right? My handwriting might not be readable, but I think I have read all these points in a very proper way. Database management, metadata storage, scalability, real-time backups, and data security. So that's basically the difference between vector index and vector database. Now, how does a vector database work? What is the like in the previous video I told you, right? Vector databases use some technique called as locality sensitive hashing. Why this retrieval process is slower in traditional databases and faster in vector databases? We'll be studying in the next videos. Hi. In the previous video, we studied about the difference between vector index and a vector database. Let's try to talk about the next topic, which is how does a vector database works? Vector database works. Okay, let's try to talk about it. First of all, if I divide data is mostly divided into two things. One is scalar and one is vector, right? Again, these are pretty basic things. You should be able to know what exactly is a scalar data and what is a vector data. We all know traditional databases, right? All the traditional databases includes MySQL, MS SQL, Oracle SQL, and so on, right? These are all traditional databases. Then comes a bunch of NoSQL databases, which is MongoDB, Cassandra, Apache Druid, and various other things, right? Snowflake, various other things. We all know how traditional databases work, more or less, right? They mostly store strings, they store numbers, they store other types of scalar data, basically in rows and columns format, right? These are the information being stored, right? On the other hand, vector database operates on vector data. So for vector data, we have special vector databases. Okay, there are a bunch of vector databases that I can talk about. Nowadays a lot of startups are actually, a lot of vector database startups are opening up. So there are a lot of vector databases. I know some of them. Pinecone is one of them. um, Atlas is one of them, and there are various other vector databases. It's difficult to remember the names. I usually go for Pinecone. I do have deployed a lot of generative AI applications for my company and for various freelancing projects. I usually go for Pinecone. It's a very simple vector database. We go for that. I will be explaining you and showing you Pinecone as well, so do not worry about it. So as I told you, vector data is basically stored in vector databases. So in traditional databases, we are usually querying. We are usually, let's say we have a SQL database. How do we query? We query using a statement like this, right? Select star from blah 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 from blah blah blah, right? So we are querying for rows in the database where the value usually exactly matches our query. So let's say select, maybe I'll just write a statement. Let's say select first name, last name, salary, blah blah blah, or just simply select star from table name where um, gender equals to female, for example. Now what's happening here? We are potentially going and trying to fetch records where the gender is having female value. So we are basically querying records, rows, right? Where the value usually exactly matches our query. In vector databases, it does not work this way. In vector databases, we apply a similarity matrix. So imagine you have a vector DB. When your query is being passed, you basically convert your query into vectors. In your vector databases, you have millions and millions of vectors, right? Vectors are could be something like this: 0 0.1, 0 0.3 something, 0 0.1, 0 0.9, 0 0.5. So it's multidimensional. This is also multidimensional. So in a vector database, what happens is we usually don't go for a like to like approach like this. We usually use a similarity metric to find a vector that is most similar to our query. So a vector database basically uses a combination of different algorithms. One of the algorithm that we can talk about is ANN. Now this is not artificial neural networks, that is with context to deep learning. Here in this context, ANN is basically approximate nearest neighbor. One of the similarity search technique that you must be aware of if you have gone through NLP classes is cosine similarity, right? So cosine similarity is also one of the techniques, but usually we go for ANN approach. Now there are also different type of algorithms, different type of approaches, or different type of um, search options are available. So for example, there could be searching through hashing, quantization, or graph based search. So we will also try to talk about hashing, how hashing works in a nutshell in the upcoming videos. So multiple algorithm, let me write it down. What are the different other algorithms? So ANN in punch with hashing, um, quantization, etc. Okay. Now, these algorithms are assembled into pipeline that provides fast and accurate retrieval of the neighbors of a queried vector. So whenever you are querying something, when you are going to the database, you are basically finding the nearest neighbors of this particular query from the contextual information, right? Since the vector databases provide approximate results, the main trade-offs we consider are between accuracy and speed, right? There could be a scenario while fetching the output, there could be a delay. So that is a major concern. Apart from that, the queries that are being returned might not be 100% accurate. So accuracy and speed are the two major concerns in a this thing, in a vector database retrieval process, right? The more accurate the result, the slower the query will be. You can also fine tune your techniques using coding, while there are some prompt engineering techniques, there are various other coding techniques that you can use to improve the speed. If you improve the speed, your accuracy will decrease. If you improve the accuracy, your speed will decrease, as simple as that. But eventually, as a data scientist, as an AI engineer, your task is to create a good system that can provide you ultra fast search with near perfect accuracy, right? So if you ask me to draw a simple common pipeline for a vector database, pipeline for a vector db, this is how the pipeline will look like. So we have let's say we have vectors, okay, and then comes indexing. So there has to be some sort of indexing that has to be done. In traditional SQL databases also, we provide indexing, right? Then we have the vector database, okay, and then we have the querying, and then finally we have the post processing. Okay, so what is indexing? Indexing is a very common technique. I think most of you might know if you know the basics of SQL. Vector database indexes vectors using an algorithm such as there are some algorithms based on which indexing are created, which is PQ, LSH. We will be talking about some of them in the future videos, or maybe HNSW. For now, learn the jargons. We will be talking about the full forms in the coming videos. This step basically maps the vector to a data structure that will enable faster searching, right? So imagine this way, if you simplify this process, so eventually your vectors are being stored in your database, right? So you have to create different indexes, different buckets, okay? Now when a user query comes in from the vectors, we have to use a intelligent technique to not go through the entire vector database and search. You can rather search in the required buckets. Let's say you can actually search it from this bucket and you will get the answers. So you don't have to query different buckets to save time. We will talk about this in details later. The second thing is querying. What do you mean by querying? The vector database compares the indexed query vector to the indexed vectors in the dataset to find the nearest neighbors. Okay? And then comes post processing. What is that? In some cases, the vector database retrieves the final nearest neighbors from the dataset and post processes them to return the final results. This step basically can include re-ranking the nearest neighbors using a different similarity measure. So post processing can also be done. So that's all about it. Next video we shall be jumping into some of the technicalities of hashing techniques and various other things. Hi. So far we already have a good understanding on how vector databases work. We also have an understanding on the differences between vector index and a vector database. If you remember, one of our use cases that we covered after we completed RAGs was we built a chatbot using a research paper. So research paper was our custom data set based on which we converted the data, we divided the data into chunks, into embeddings, and then we were using FICE as a similarity search technique, which was nothing but a vector index, and based on that we were able to get the answers, right? If I go back to the architecture, just repeating once again, what happened was we took a research paper, we divided the paper into different chunks, we created the embeddings, and then we were using a vector index. So let's say I will write it down as vector index. And when user was asking a query, we were doing the same thing, converting the query into vector index, into vectors, and then we were doing a search, like we were using FAISS, the Facebook AI similarity search, and we were getting some related vectors, and using chat completion we were giving the output, right? Everybody remembers that. If you haven't gone through that video, request you to go through that video. Now in this particular video we are going to focus on vector database. Instead of vector index, we will be using a vector database. Now there are different vector databases. I will be taking the example of Pinecone for this particular series, for this particular video. Now to get started with Pinecone, you just have to go to pinecone.io. Mine is already logged in, but you can easily create your account, sign up for the account, and you should be able to come to a page like this. In your case, there will be no indexes. I have already created a simple index, which is a rack demo index, and this was done as part of my trial. Now on your screen, immediately I will be creating a new index, and I will be using that to store the vector data into that index. So eventually what I'm going to do is, the flow remains the same. Instead of in-memory index, we will be using Pinecone. I will be creating a Pinecone index, and we should be able to store all the vector data into Pinecone index. And when a user is asking something, we should be able to go to this index, get the relevant information, and give the final output. Let's go ahead. So we had written the code till here, if you remember, right? Now I have written down few lines of code, of course not entirely, but just few lines of code, and then we will proceed from here. So from LangChain community document loaders, I'm just loading the rack paper. Okay, because I restarted my notebook, it's asking for installation. So once the libraries are installed, I will be doing the same thing. I will be loading my paper, and I'm getting all the pages. Done. So yeah, my pages are loaded. Okay, so yeah, I just have to rerun everything. So we should be able to finish rerunning all the pip installs within a couple of seconds, and then we will proceed. As I'm using Google Colab, I have to install it every time, but when it comes to real-time production level code or production level projects, or when you're using AWS or Azure, you don't have to install the libraries again and again, right? Even if you're building this locally on Jupyter Notebook or on any other IDs, you don't have to install these libraries again and again. So once these libraries are installed, I'll go back to this and I will try to rerun the code. And here we all have all the pages from our research paper, right? What exactly is Pinecone? Pinecone is a vector database that helps, or in simple terms, we can actually store and index text data as a high dimensional vector in Pinecone. Pinecone is nothing but a vector database, right? If you want to see this particular file, I can download it and I can show you. So this is my research paper, right? Retrieval augmented generation for knowledge intensive NLP tasks. It's a 19-page document. It has certain amount of tokens. We will be breaking down and we will be converting it into vector data, and we will be storing it in Pinecone vector database. Moving ahead. So here I have done the splitting the PDF. So since we can't use the entire PDF as the context for the model because the entire PDF is too huge, a potential solution is to split the PDFs. So I'll go back to Miro. So So what's happening is I have a PDF document, right? Now I'm going to split it. So after your splitting is done, let me just run this file. So recursive character text splitter is done. Chunk size is 100. Chunk overlap is 20. Now you can see my first document is this. My second document is this, and so on. Right? Now, what is the meaning of chunk size? Chunk size basically means if you have a PDF, let's say the PDF is of let's say 1000 tokens. Chunk size of 100 means 100 tokens, different chunks will be created. As simple as that. What is chunk overlap? Overlap means the last, let's say here the chunk overlap is 20. So the last 20 will be a part of the next document as well. Right? So imagine, let me go to a simple blog and show you. Let's say I'm going to this blog. Now let's say my chunk size is 50, for example. Let's say these are my 50 characters or 50 words, 50 tokens. Okay, imagine these are my 50. Let me just okay. Now what I'm trying to say here is, let's say till here is my 50 chunk size. Okay, 50 chunk size or 50 tokens. Now these 50 tokens will be part of my first chunk, and let's say my overlap size is, let's say 20 or maybe 10. So let's say these 10 are these. So this with the next 50 tokens, let's say till here, will be a part of the second chunk. I hope this is clear. It's very simple, right? And that's how I'm breaking down my entire PDF into different chunks. Now this is just for showing, but in real-time scenarios, our chunk size should not be 100. It could be 1000, it could be 2000. Based on your experience, you will automatically understand what should be the chunk size. Okay, so my bad. Let me go ahead, and so for our specific application, let's use 1000 characters instead. And here what I will do is I will do a text splitter is equals to, instead of 100 I will take 1000, and chunk overlap could be 20, doesn't matter. Documents is equals to text splitter dot split documents, and I will be passing my pages. Okay, this is done. Then I can print my documents. So it will have 1000 characters in one particular chunk, right? Now, given a particular question, we need to find the relevant chunks from the transcription or from the document to send to the model. Here is where the idea of embeddings come into the picture. What is an embedding? Embedding is nothing but a mathematical representation of the semantic meaning of a word, sentence, or a document, right? It's a projection of a concept in a high dimensional space. Embeddings have a simple characteristic. The projection of related concepts will be close to each other, while concepts with different meanings will lie far away, right? So to provide with the most relevant chunks, we can use the embeddings of the question and the chunks of the original document to compute the similarity between them, right? So what's happening here, I'll move to this one. So from your PDF, first of all, you are dividing the data into chunks. Then data is converted into embeddings. and just imagine you are storing it in a Pinecone vector database. So when a user is asking a question, question is also converted into vector. Then you go and search. Now imagine here you have hundreds and thousands of vectors, right? While searching, you got to know that the most relevant information is here and here. So as a retrieval operation, you get two vectors as an output. And from these two vectors, there is a chat completion, and then the user gets the final output. This is how the entire flow works. Okay. So the next step will be, let's say from LangChain embeddings.openai import OpenAI embeddings. I will be creating embeddings. Let's say embeddings equals to OpenAI embeddings. Here I will pass my API key. What is my API key? I already have a OpenAI API key, and then embedded query is equals to embeddings dot embed query. What is the full form of rack? Okay. So let's say I will be printing, let's say printf embedding length. I'm going to print the embedding length of embedded query, and also print embedded query. OpenAI API key is not defined, so I'll have to move up and try to define it. I'll scroll down. Yeah, because I restarted my my Google Colab, so it has gone. You can see my embedding length is 1536. Okay. Now, and you can see these are my few embeddings. Okay. Next, what I'm going to do is, let's say, to illustrate how embeddings work, let's first generate the embeddings for two different sentences. Let's take some random examples. Let's say I will take my first sentence is equals to embeddings dot embed query. Let's say my sentence is I love to watch YouTube videos. Similarly, sentence 2 is equals to what is racks? What is rack? Then what I will do is, let's run this. Now let's try to compute the similarity between the query and each of the two sentences. Okay, so here we can use a cosine similarity approach. I hope everybody knows cosine similarity. If not, please go back to NLP videos, watch it out, and your doubts will be clarified. So let's say from sklearn.metrics pairwise import cosine similarity, distances similarity. Let's say query sentence 1 similarity is equals to cosine similarity between my embedded query I hope there is no spelling mistake, embedded query with respect to the sentence 1 and okay, my similarity score is something like this. Similarly, I will do it for the second one, sentence 2 and I will also print my sentence 2 similarity. And you can see the similarity score of the first sentence, which is completely random sentence, right? The similarity score is coming as 0.68. Now similarly, let's say I will take another sentence, and here I will write it down. Who is Roger Federer? Who is Roger Federer? Run this, and similar to this, I will be taking sentence 3, and printing my sentence 3 similarity. And here you go, the similarity is low. So related to RAG, the similarity search results are coming high, right? So till now, I have not introduced Pinecone. I am just repeating what I have already explained in the previous videos, right? We have used in-memory vector store. In practice, we need a vector store that can handle large amounts of data and perform similarity searches at scale, right? Because working on a simple project where you are just dealing with one or two PDFs, you can always use vector indexes. But when it comes to complex use cases, complex projects dealing with thousands and thousands of PDF documents, you want a production friendly product, then vector databases are needed. So the first step is to create a Pinecone account. So let me just write it down, set up Pinecone. Before we release this entire document, I will also write down few comments so that it is easier for you to understand, right? So to set up the Pinecone, what we need to do is we need to go to Pinecone and we need to start creating an index. However, my previous index is already created, but I will be creating a new index so that we can test it out on that. So let's say test index. Dimension has to be same like your embeddings. Embedding length is 1536. It is always better to keep it 1536. Which type of metric do you want to use? Euclidean distance, dot product, or cosine? We'll keep it cosine. And all the other things I will not change. I will create the index. So my index is created. Okay. If I go back to my indexes, I will be using the test index. Got it? So from Pinecone, so these are the two things. API key, let's say I will be using let's say I'll directly use PC is equals to Pinecone, API key is equals to something. That's it. So where to get the Pinecone API key? You have to go here. In my case, I think I'm using this one. Yeah, I'm using this one. In your case, you can always create a API key to work with this. Okay, so let's say I will be creating this API key. Done. My Pinecone is ready. From Pinecone, import serverless spec. So let's say cloud is equals to AWS and region is equals to, let's say, US East 1, US hyphen East hyphen 1, US hyphen East hyphen 1, and then spec is equals to serverless spec. This is not needed, but just in case, cloud is equals to cloud, region equals to region. Done. If you have environment variables, you can always write it down like this: os dot environment dot get. If you have, let's say, Pinecone cloud or AWS, something like this can also be done if you have your own environment variable. Okay, as in my case, I don't have an environment variable. Let's say Pinecone underscore region. So I will be using these hard-coded values, right? My spec is ready. I will be writing down my index. Let's say my index name is equals to test index. Okay, this has to be the same name like here, test index. Done. We can always do a check, something like if your index is not present, you can create an index on the go. So basically this step of creating an index is not mandatory. If you are creating from here, it is well and good. If you don't want to create, you want to create directly in the code, that can also be done. So let's say if index name not in pc.list indexes dot names, then pc.create index with index name and dimension is equals to 1536. Now here also, if you don't want to hard code, you can always take this number, length of your embedded query, and directly pass it here. Okay, here I'm just taking hard coded numbers, and then metric is equals to cosine, spec is equals to spec, and then index equals to pc.index, index name, index.describe, stats. Okay, my index is already there, so it is able to get the dimension and all those things. Now what you need to do is, as we are using Google Colab, we need to authenticate our Pinecone. Okay, so authentication. So to authenticate, wherever you are stuck with these kind of codes, you can always use ChatGPT. But the thing is, all of this code keeps changing. Like honestly speaking, I already had a video or a code prepared on Pinecone, but the same Pinecone code, when I ran it today, I was not able to run because there are a lot of changes in Pinecone. So by the time you are actually checking this video, some of these codes might not work as well. So in that case, what you need to do is you need to either go and check the LangChain and Pinecone documentations, or probably go through Gemini or GPT-4 to kind of check whether they have the latest codes. So this is a hit and trial process, right? The same way I have also done. So authenticate. Now here it will be asking, okay, Pinecone notebooks. Pad Pinecone notebooks. Yeah, done. Now authenticate. We should be able to get the Pinecone. I will be able to authenticate using the same account that I'm using here, and then I'm able to authenticate. All set. Now from LangChain Pinecone import Pinecone vector store, and after that I will do doc search is equals to Pinecone vector store from documents, and I'm going to pass my chunks. Remember, chunks are nothing but, if you go back to your code, right? What are chunks? Right? Chunks and embeddings. Index name is equals to index name. Run this. Okay, chunks is not working because I have not run the previous codes. So I'll just go back. Okay, now I'll go back and run this code, because in the middle some of the codes were not executed as I restarted my Google Colab. So my doc search is ready. Pinecone vector store from documents. Now I'll go back to my index and I'll try to see. You can see indexes are created, right? How many indexes are created? Sorry, how many vectors are created? 92. What does that mean? What do you mean by 92? Try to remember this thing, that this was your paper, right? Now we had taken 1536. 1536 was your embedding size, but your document chunk size was 1000, right? So somewhere around 92,000 tokens are available in this particular document. That's why you are able to see 92 vectors. So 92 vectors are created. So if you go back to Miro, here in fact there are 92 vectors, vector 1, vector 2, dot 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 92. So from this PDF 92 vectors are created. Okay, done. Now after this, as retriever, yes, we are able to get this retriever, so it is working fine. Now what I'm going to do is I'm just going to go to the previous codes of the conversational thing, this part. I'm going to just copy paste this, and I will again go back to copy paste this part. Okay, now what I'm going to do, what are the changes I want to do here? As a retriever, I want to use this as a retriever, right? Everything else remains the same. Now I will run this, and then I'll run this. So I don't know, I don't have enough context. Now if I ask what is RAG, for RAG it will be able to generate the answer. So I hope everybody is clear. We had the PDF, we divided it into chunks, then embedded vector embeddings, stored it into Pinecone. If you want to visualize and see, you can go to your Pinecone index. You will be able to see 92 vectors. Now remember one thing, each vector, you can see there are 92 vectors here, right? What you can see here is a score. What does this score means? This score basically means that for this particular vector, with respect to the entire data, what is my similarity score? So your similarity score is something like this. So internally from these vectors, when you're asking a question like what is RAG, what's happening is the query goes here, what is RAG? You are converting it into vector data, and then you are searching it in all the 92 vectors, and let's say you get 3, 4 or 5 vectors that are closer to the question. You take that and then you do the chat completion, and then you finally get the output, and the output is visible here. So that brings to an end to this session on vector database. Regarding RAGs, you already know what are RAGs. We already have done this exact project without vector database with vector indexes. Now you already have a knowledge on vector databases. You can always go back and play around. Always make sure whenever you are doing these kind of activities, whenever your task is done, please go back and delete your indexes, because eventually each and every query that will be used, it will be chargeable. For now I have not added any kind of credit card. I am using a starter usage. That's why my usage is very low. Obviously I will be deleting all these indexes. So in order for you to test this out, you have to do the same steps, create your own indexes and practice it out. That's it. We can always take this project to the next level by converting it into Flask applications or Streamlit applications, something like these. Let's say one of my applications was this, right? So these kind of fascinated Flask applications, we will be covering that as part of the final projects. But for now, that's all about this video on vector databases. Hi. So far we already have a good understanding on vector databases. We also know how things work. Just repeating once again, when you're working on a custom document, you have a PDF document, then what happens is you are chunking it down, right? You're creating different chunks. From different chunks, you are converting them into vectors. And then these vectors are getting stored in vector databases. I will write it down as VDB, right? Now, when a user is asking a question, the question is also broken down into vectors, and then you are doing a search. So the search operation happens here, and then from the vector database you get some relevant information or relevant vectors, and then from there you do the chat completion and get the final output. This is how things work, right? But if you go back to the very initial videos, we talked about the differences between traditional database and vector database. I also told you that vector databases are faster because vector databases are meant for vector data. Traditional databases are usually meant for static data, not for vector data, right? But the search in vector databases are also faster as compared to traditional databases. How? Because they use some, multiple type of algorithms. And one of the classic algorithm I talked about is approximate nearest neighbors, or using locality sensitive hashing. So various concepts are being used. Okay. I also give you a brief idea. When you're storing the data in the vector databases, you're basically storing it in different buckets, right? Some vectors are stored here, some are stored here. So when you're actually asking a question, you are in fact just going and referring to certain buckets, not the entire database, because of which the search operation is faster. But what exactly is this algorithm? Let's try to talk about LSH. What is LSH? LSH simply means locality sensitive hashing. Locality sensitive hashing. Now there are different types of hashing technique. Okay. There is cryptographic hashing. There are various different types of hashing. Let's try to focus only on the LSH, locality sensitive hashing. Now let's say I have 4 tokens. Let me just bring it a little bit down. Now let's say I have 4 tokens or 4 sentences. T1 is hello world. T2 is world hello. T3 is, let's say, big small, and T4 is nothing but small big, something like this. Now what happens is this entire process goes through a LSH process, and based on that your final database will have different type of buckets. All the similar texts or similar documents will be stored in one bucket. Let's say T3 and T4 is stored here, and T1 and T2 are stored here. So LSH is basically used to find similar data points when the data set is too large or in higher dimensions. Okay, so let me write it down. LSH used to find similar data points when data set is too large or in higher dimensions. Now talking about the aim, it has a single, there are 2 aims, majorly 2 aims. One of them is minimize the probability of collision of similar items, and the second one is reducing the number of comparisons. Let me just expand it. My bad. Right? These are the 2 different aims of LSH. Minimizing the probability of collision and reducing the number of comparisons. Now let's try to divide this task. What really happens in the background. Now imagine these are documents, right? Document 1, document 2, document 3, document 4. So imagine you have a document. So with the very first step is nothing but shingling. Mathematically, I will explain what exactly are these steps. After shingling comes min hashing. And then comes LSH. So what exactly is shingling? So it's nothing but a set of string having length k that appears in documents. Now imagine you have a huge document, hello comma world. Imagine you take a k value as 2. K means grams. So let's say I'm taking the n grams as 2. What will happen? My document 1 will be broken down into hello and comma world. Well, this is just a hypothetical example. We know that comma is not treated as a token, but imagine you have a larger word. Okay, imagine the larger word is hello, how are you? Now what happens here is, taking this as an example, when you are performing shingling on k is equals to 2, this basically becomes hello, how are you? So 1, 2 and 3. That is basically shingling. Now what is minimum hashing? Minimum hashing is nothing but signatures, short integer vectors that represent the sets and reflects their similarity. Okay, and finally we have the LSH step, which is nothing but finding the candidate pairs, those pairs of signatures that we need to test for similarity. Okay, lot of theoretical part. Well, we use a concept called as Jaccard index. And what is the formula of Jaccard index? It is A intersection B divided by A union B, the modulus value. Let's take an example and try to solve this problem. Okay, it's not that difficult to understand. So we have a new screen. Let's write down the Jaccard formula again here so that we don't forget. Jaccard index formula is A intersection B divided by A union B modulus operation. Okay, now let's say I'm going to take examples. I'm going to take two sentences. Okay, so let's say my sentence 1 is let's say I love rag. My sentence 2 is rag is important. And my sentence 3, let's say my input query is what is rag. Okay, so I hope this is understood, right? Now first of all, what is sentence 1, what is sentence 1, and what is sentence 2? These are input sentences, input documents, right? Let's say you have two input documents, you are vectorizing it and you are storing it in your vector database, right? And user input is what is rag. We need to basically find the similarity between this with this and this with this. Simple. So the very first step is my shingling step. Shingling step. Now shingling basically involves the breaking down of the sentences into smaller overlapping substrings, or called as shingles. For example, if we use a shingle size of 2, let's say bigrams, we can convert my sentence S1 into I love rag. Similarly, my sentence 2 will be converted into rag is is important. And what about my query? My query represented by Q is going to be what is rag. Now these two are same, right? Is rag and rag is are same. Now these are your shingling. What are shingles? These are your shingles, right? Okay. Now calculating the Jacquard similarity. So let's say my step 2 will be calculating the Jacquard index. Okay. Now Jacquard index is basically calculated as the size of the intersection divided by the size of the union of the sets. The formula is already mentioned here, A intersection B divided by A union B, modulus operation. So what will be the Jacquard index of my sentence 1 with respect to my input query Q? Now how many intersections do we have? S1 intersection Q. How many commonalities? There are no commonalities, so input is empty. What will be the union operation? The union operation will be everything, these two and these two, right? So there will be 4 elements. So what will be the formula? The formula will be 0 by 4, modulus operation will be 0. Got it? Similarly, what will be the Jacquard index of S2 with respect to Q? So S2 intersection Q is going to be rag is, or you can say this one. So it's going to be 1. And what is S2 union Q? It's going to be 4, right? Elements, 4 elements. So what will be the Jacquard index? It will be 1 by 4, which will be 0.25. So clearly sentence 2 is more closer to the query. So if you ask what is rag, probably it will do a chat completion based on sentence 2, which is rag is important. That is all about LSH. So and the final step after calculating the Jacquard index, the final step is the LSH. Use LSH for efficient similarity search. Locality sensitive hashing helps in efficiently finding similar items by hashing them into buckets, right? So there are multiple techniques. One of them is min hashing. Creates a signature for each set of shingles. This involves applying multiple hash functions to the shingles and selecting the minimum hash value for each function. Or binning. Group the signatures into buckets. Similar items will likely end up in the same bucket, right? And based on that only you finally create your final buckets. So whenever you have an input document, you convert them it into multiple vectors, and then using this technique you pass them into different buckets. And when a user query comes in, you do the Jacquard index and then find and then go and search just the relevant buckets, not the entire buckets, right? So in this particular example, after calculating the Jacquard index of sentence 1 and sentence 2 with respect to the input query, we identified that S2 is closer to the user query. So this method allows for efficient comparison, especially when dealing with larger data sets, as LSH reduces the number of comparisons needed by focusing on likely candidates. And that's it.